10 more seconds. Go live to YouTube, then I mute YouTube, so there's no echo. Then I share my slides to you. So everybody see my slides now? Please confirm that you are seeing my slides. Do you see my slides? So I need one respond, please. Do you see my slides now? Because I open a lot of slides, so I want to be sure that you are watching what I'm talking about. So Assam or anyone from Egypt or Lebanon can.
Yes, Dr. Ahmed, you can start.
I mean, you see my slides, right?
Yeah,
you see my presentation, right?
Yes, I can see it, yeah.
Okay. Okay. Hello, everyone. First, I appreciate the opportunity that OPA gave me to introduce this interesting topic to you. Today's topic will be introduction to organic shale evaluation and development. And actually, I teach this topic in one semester. So today, all what we'll do, I will give you a short presentation about it. Hopefully, you will like it. Okay, so I will go through what is shale evaluation, what is drilling pad, what is shale completion, and finally we'll end by a conclusion. Then I will be ready to take your questions. Okay, so first, what is shale? Shale is a dense sedimentary rock. So for sure, we produce oil and gas from a sedimentary rock, okay? But the special thing here is that now we are producing from the source rock itself. If you got a class in geology before, they will teach you that we have a source rock, then a migration, then for millions and millions of years, that organic content there under high pressure and high temperature, it become hydrocarbon, right? And to start migrating from the source rock, and it goes to a trap. The trap may be sandstone formation, maybe carbonate formation. This is what we call it a reservoir, a conventional reservoir. But today we are producing from the source rock itself. So the source rock in this case is shale. And today I will teach you how to produce from shale, not from the sandstone formation or carbonate formation, what is you already know about and you already get a lot of courses about. Okay, that organic shale, from its name, I'm saying organic, so for sure there is organic material inside it, trapped inside it. But the main problem, it is extremely low permeability. It is really very, very low. It is nanodarcy. We measure permeability, in conventional reservoirs like, millidarcy, but in shale, we are talking about nanodarcy. So it is something like, 10 to power of -9 or something, okay? So for this situation, to develop that shale, I must do horizontal drilling. Look, it is not an option. You must do horizontal drilling. Second, you must do hydraulic fracturing, multi-stage hydraulic fracturing, massive hydraulic fracturing, huge job, okay? And finally, we should use something we call slick water as a frac fluid. I believe many of you don't know what is slick water, but at the end of, after let's say 20 minutes, I have a slide about the history of slick water, so you'll get enough information about what is exactly slick water. Okay, so I got question why organic shale is important. Simply, a country like United States, they produce more than 50% of the oil production from shale. Do you know how much is that 50%? It is more than 5 million barrels a day from only United States. China, they produce from shale. Argentina, they produce from shale. Maybe no country in the Middle East produce from shale, and I will tell you why later. Please remember this question. If I forgot to tell you, it would be nice if any of you wrote me this question at the end. Okay, so why we don't develop organic shale in the Middle East, in Lebanon or in Egypt or in Saudi Arabia, for example. So as you see here, the Permian Basin, this is in West Texas and east of New Mexico. Bakken, this is in North Dakota, and all of these things, Eagle Ford, south of Texas, all of them, they are just shale formations. If you count, you will find more than 50% of United States oil production coming from shale. United States produce around 13 million barrels of oil every day. Shale plays or locations that we have organic shale almost everywhere in the United States. There's a lot of many shale plays in the United States and in Canada also. Okay. So let me tell you something about how to evaluate a good shale play, because we have a shale play in, let's say, many shale plays in Egypt, or maybe we have many shale plays in Lebanon. But the question is it feasible or not? Is it good ones or not? So let's tell you something about how to give that judgment. Is it good or bad? Okay, so this is like the list of the topics. So let's get it started quickly. First you need to cooperate with the geologist. At this stage, you need to deal with the exploration team, which is almost a lot of geologists. Okay, so a lot of geologists, petrophysicists. So it is not kind of engineering job at that level, but you need to be involved in that. So we need to do something like basin analysis to know exactly how the hydrocarbon formed and what is the passes of that migration. Okay, so I need to know where is the source rock, where is the conventional reservoirs. So later I will ask myself, if I go to these source rocks, is it good ones or bad ones? Is it what I can call sweet spot? Sweet spot is a good place in a shale, so I can, put my drilling rigs and, drill wells and do hydraulic fracturing and frac and produce. So that good place, we call it sweet spot, shale sweet spot. Also, you need to ask yourself about the geologic timing. Is it the source rock in that place? Is it Cretaceous, Jurassic, or something else? And still, this is kind of geology job, not engineering job. Also, I need you to, if you see a log for a shale, I need you to know how to evaluate if it is a good shale, organic shale or not. So we expect to see high gamma ray. You will tell me what is special. We all know that in gamma ray, in shale, we have high gamma ray. Yeah, no. You will see gamma ray higher than expected. Okay, why? Because that organic matter includes some extra uranium. Okay, so you'll see more radiation. Also, in that shale, you will see higher resistivity, more resistivity. Why we have more resistivity? Simply because there is hydrocarbon inside that shale. If there's hydrocarbon, you will see high resistivity. Make sense? I believe so. Okay. Also, we should have good porosity. If you don't have a good porosity, it means you don't have enough hydrocarbon to produce feasibly. So economic-wise, it will not be a good decision to develop that place. Okay, so we should have a good porosity because that porosity can give me a measure about how much hydrocarbon I have in that place. Also, I should have a good TOC. TOC stands for total organic carbon. This is a measure by percentage for the organic contents you have in that place. Okay, and there is two famous techniques named after two scientists, two researchers who published papers about these techniques, Passy, and the second one called Smoker. So Passy and Smoker, both of them, they have a method to measure the TOC only from the logs. Is it accurate? For sure, no, it is not accurate. But if you want something accurate, you need to do more logs, you need to invest more money. So at that stage, only I have some wells drilled in that place for conventional reservoirs, and I have some logs, and now I'm evaluating these logs. Okay, so this is the maximum you can do at that stage. It's just to use some correlation developed by Passy and Smoker, and you can tell me something about your expectation for the TOC. Is it 4%? Is it 3%? Is it 1%? And this is good or bad. Also, we need to know something about the maturity, the thermal maturity. This is the effect of pressure on temperature, how that organic content get cooked. Is it well done, rare, or intermediate? Like when you go to a steakhouse or a restaurant, when you order a meat or a steak, they ask you about how good how the cooking you want. Is it well done or rare or intermediate, medium? Okay, so the hydrocarbon has something similar. If it is well done, it will be gas. If it is intermediate or rare, it will be condensate or oil. Okay, so this is important to know. So I want to show you something, a good piece of work done by one of my advisors. His name is Richard Bateman. He's a British guy, but he was teaching at Texas Tech University, and I was one of his students. So he presented to us something very interesting that summarize a lot of information. Look to the mouse, the first one to the left, 9 components model. This is all the 9 components exist in the rock and what is inside the rock. So this is the rock and this is what is inside the rock. So all together, and I can use all of that to get the bulk density. Let's check that. We have organic matrix. We have inorganic matrix like the sand, the carbonate. We have the clay solids. This is the clay contents. Okay. We have how many? 6 different liquids inside that, not liquid, fluids inside that rock. Look, we have free water, we have cap-bound water, we have clay-bound water. This is the 3 different types of water we have inside the shale or inside any reservoir, any conventional reservoir. Look to the other side, we have oil, we have free gas inside the porosity of that space. Also, we have absorbed gas, a gas absorbed in the solid surface of that rock. Okay, so these are the 9 components we have at any rock, and I'm also showing the the fluids and the rock itself. Look to the next one. 9 components wettability. This side we have free water, bound water, clay water, and for the clay solids and inorganic matrix, this is like water wet. Look to the other side, the organic matrix. We have oil, free gas, absorbed gas. This is oil wet. I know you get the wettability in your college, but here just we are summarizing a lot of information, and I believe this will be helpful to you to let you imagine the rock, even if it is conventional or unconventional. Okay, look to the next one, 7 component with hydrogen. The neutron log, it is only anything that has hydrogen. So it can see free water, the 3 types of water. It can see the 3 types of hydrocarbon. Also, it can see the organic matrix. All of these things have hydrogen. For the resistivity or the conductivity, the electric conductivity, I can get the 3 components of water. And finally, for the gamma ray, the radiation, the organic matrix, I told you it has some extra uranium, so it has some radiation. And also the clay itself has some radiation because of the, uranium, thorium, and potassium. Okay. For the well logging, I believe you get a class in well logging. There is something we call triple combo. Can anyone tell me what does triple mean? Look to the screen. Triple is 3. Count, gamma ray, 1, resistivity, 2, density, 3, neutron, 4. They are 4 things. We are measuring 4 things. So why we call them triple? They are 4 items. They are 4 logs. So why we call them triple, which is 3? Simply because the density and neutron, both of them, they are measuring the same thing, which is a porosity. So porosity is 1, resistivity is 2, gamma ray is 3. This is why we call them triple. If you add sonic to them, sonic, which is using dipole sonic, for example, the sonic wave, we call it quad combo. Quad means 4, but if you count them, you will see 5 things. Okay, why? The same reason, because the density and neutron, both of them, they are measuring their porosity. Okay, why I'm teaching you something about conventional well logging? Simply because for shale, we need to do some special well logging. Like Geochem Logging, we have a tool that measure the elements inside that formation. And the tool itself can translate these elements into minerals. So if there is, let's say, 5 different minerals, all of them has aluminum, or all of them has carbon, the tool, using data mining techniques, can translate each mineral to the right, each element to the right mineral. Okay, so that tool, we call it Geochem Log. There is many companies working in that business. So we have Flex, this is Baker Hughes. We have GEM, this is the name of that tool name. Flex is Baker Hughes, GEM is Halliburton, SES and Litho Scanner, this is Schlumberger. Okay, all of these tools, again, they tell you exactly the minerals inside the formation. Okay, so no conventional logging can tell you that. Okay, something else, the MRI log, which is sometimes we call it NMRI log or MRI log. You know, if you are playing soccer or football and you broke your arm, you go to a doctor, he will do X-ray for you. Why X-ray? Because the X-ray can see the bones, but the X-ray cannot see the fluids inside your muscles, right? If the injury you get not in the bone, but the injury in the muscles, X-ray will not help. You must do magnetic resonance imaging, MRI. If someone has a severe headache for a long time, and he go and see a doctor, the doctor will tell him, hey, you need to do MRI for your brain just to be sure that there's nothing wrong there. There's no, there's nothing bad, or in the brain itself. So the MRI can see the fluids inside something. So why we are doing MRI for shale? Simply to get information about the quantities of the fluid inside the rock, the volumes, also the properties of these fluids. I can know exactly these fluids, if it is water, or if it is gas, or if it is oil. So I can know exactly the type of the fluid, okay, using the NMRI log. Also, I can know the size of the pores, so I can get a perfect measure for the porosity, and I can get a perfect measure for permeability. Not only that, I can also get accurate measure of what is producible of these fluids and what is not producible, which is something like a magic. Okay, this kind of tools are very expensive, but during the evaluation stage for shale, we need to do that. We need to do that. Okay, so I told you about the Geochem log to get the mineralogy of the formation. And now I told you about the NMRI that tells you about the fluids and permeability and porosity of that formation. The NMRI, it measures something called the relaxation time, T1, T2, and diffusivity coefficient. And based on that, I can differentiate between different types of hydrocarbons, different types of water, and so on. Okay, so this is very, very helpful tool. Okay, then I should do coring. Imagine the organic shale is 300 feet thickness. The thickness of the shale formation is 300 feet or 500 feet. Too thick. Do I need to core all of it during evaluation? Yes. You need to core all of it, even if it is 500 feet. Okay, so we do coring, full size coring, like as you see in the picture. And we do this to serve two jobs. First, rock eval company. There is a Geochem lab company will take some smaller cores to test the TOC, to test the S1, S2, S3, and I will tell you exactly what is that, very soon. And also there is a second company do the geomechanics of the rock mechanics testing. I need to know something about the Young's modulus, Poisson's ratio, these kind of mechanical properties, because this kind of things very important to do a good design for a hydraulic frac job. Okay, so for the rock eval, this helped me to evaluate if this sweet spot or this location is good or bad, and the rock mechanics will tell me something about how to optimize my hydraulic fracturing job. Okay, here is the Geochem lab or the rock eval. As you see here, pyrolysis testing, I'm heating something until I burn it. Okay, look, here is the S1. S1, this is like the amount of free hydrocarbon, gas or oil in the sample under testing. Okay, the S2, look, this is the S1, look to the mouse, this is the S1, here's the S2. S2 is the amount of hydrocarbon generated through thermal cracking of non-volatile organic matter. So the carrier itself of the hydrocarbon, I'm burning it itself. I have a free gas and free oil. When I burn it, I get the S1. When I burn the carrier itself, the kerogen itself, I get the S2 and the Tmax. And S3, this is the volume of the CO2. Whenever we burn something, we get some CO2 at the end, okay? And so this is exactly what we do in pyrolysis analysis, or in Geochem lab company. And we do this figure. Look to the mouse again. We have a fluid inside that formation from type 1 or type 2 or type 3 or type 4. I know exactly the type of hydrocarbon I will produce. Is it gas? Is it condensate? Is it oil? So I use this figure, what we call, Van Krevlin diagram. This is the name of a guy who developed the technique. And this will help me to know exactly the kind of hydrocarbon I will produce. This is kind of a report. The table is a report I get from a Geochem lab company. Tell me the S1, S2, the productivity index, the Tmax, the TOC, the hydrogen index. And I can use these things to confirm exactly the type of fluid. Look, I'm almost know nothing about that formation. Now I'm evaluating. This is why I'm telling you I need to do a lot of extra work, extra well logs, special logs. And now I do coring, and I send these cores to rock mechanic testing. I send them to geochem testing, because I know nothing about that formation, and I need to collect as much as possible to optimize my frac design, or to decide, is it worth to invest billions of dollars in that location or not? The investment in shale, it is billions of dollars. Okay, here is to the left a table from a rock mechanics company. It tells me information about the compressive strength, Young's modulus, Poisson's ratio. Okay, this helped me to know the mechanical properties of the formation. There is something we use in shale, something we call brittleness index, and there is an equation to calculate brittleness index. This equation here, we call it Rickman equation, simply because the guy who introduced this equation, his name is Richard Rickman. He was working for Halliburton, and he published this paper in 2008. So we used to call this equation Rickman equation. He used Young's modulus, static Young's modulus, and static Poisson's ratio to calculate something called brittleness index. The brittleness index is 10%, 20%, 70%. So it is a percentage. Whenever we have high brittleness index, it means this is favorable. This is very good for the hydraulic fracturing. So we like to have high brittleness index. If you are fracking a formation, brittle formation, you will get excellent result and you will produce a lot of oil. If that formation is ductile, it is too complicated to produce good amount of gas or oil out of it. And this will affect the type of frac fluid you will use. And I will tell you how later. Okay. Again, this is a case study from somewhere in the western desert of Egypt. I believe all of you, many of you went to Egypt. So this is from a location belongs to Khalda. Before I came to United States, I was working for Khalda. So, and this is confirming that we have a condensate and oil in that location. Look, here is the Tmax and hydrogen index. Here is Poisson's ratio and Young's modulus. This tells me this formation is brittle, something like 60, 70%. Okay. Also, here's the TOC, the S2, and this is the oxygen index with, hydrogen index. All of these things confirming that we have a liquid hydrocarbon, most likely condensate. Okay. So we have high brittleness. We have oil window. It means like I'm producing oil or condensate. Also, we have a conventional behavior. Conventional behavior means what? I have a thick shale formation, but there is a tiny small layer conventional in the middle, like a small 10 feet of sand, and this sand saturated with condensate oil. So we consider that little one like a little or small conventional reservoir inside the middle, in the middle of the shale itself. Okay, so we have conventional behavior. It means we have these kind of tiny little sands or carbonate saturated with hydrocarbon in the middle of the shale itself. Okay, here is a technique we developed like a few years ago, and we call sweet spot quality index. Sweet spot quality index, I told you a sweet spot means a good place inside that shale that we put our drilling rig and we drill many hundreds of wells. So that excellent location, we call it sweet spot. But we need to have a measure or something to grade or scale these sweet spots. If I want to compare a sweet spot in West Desert of Egypt with a second one in Lebanon, with a third one in Saudi, with a fourth one in the United States, we need to have a scale for that. So this technique, we have something we call a reservoir log to the mouse, to the top of that shape, polygon. RQI, this is a reservoir quality, this is a measure for reservoir quality index. To the right, this is completion, this is conventional behavior index. If I have this kind of tiny small layers or not. At the bottom, this is completion quality index. And to the left, this is operation index. Operation index includes the price of the gas, the price of the operation, the availability of the equipment, the horsepower. There's a lot of things. So to evaluate a shale and put it in a graphical shape in front of a decision maker, if I see this, I would say, hey, it seems like this formation has very high completion quality index. It means it is very brittle formation. If I see to the right, CPI, which is conventional behavior, it seems like there is some tiny layers inside it. Just when I look to the shape, I understand that. To the other side, It is, for the operation index, this 2. It seems like the oil price is not that high, but it's still, okay. Okay. We need a high oil price to, produce shale without a problem. Especially some shale plays are very deep, and drilling, it will be very expensive. Okay. Let's keep moving. This is like a definition. Let me check that time because I don't want to, okay. So this is like a definition of what is reservoir quality index, what is completion quality index, what is conventional behavior, what is operation index. This is what I just told you in the slide. Okay. The case study to the left, this is from the Western Desert in Egypt, and I was trying to compare it with some shale plays in the United States. Marcellus, Burnett, Eagle Ford, Hinesville, all of them good shale plays in the United States. So I was trying to compare the one we have in Egypt with these things. Okay, let me tell you something special about drilling for organic shale. We have something we call drilling pad. A drilling pad is just one location, one small location in the surface, and I use it to drill maybe up to 12 wells from the same place. So one drilling location, and I drill up to 12 wells, 6. If you see the mouse, for this one, you see there are 3 wells to that direction and there are 3 wells to the other direction. I can have up to 12 wells, so 6 to that direction and 6 to the other direction. Why this is good for drilling? You can use only one rig and you can rotate. You can drill the first surface. When we drill the surface part first, then we go for the intermediate, then we go for the lateral, right? So I can drill the surface part of the first well, then I can move the rig, push the rig, walk the rig. There is a slider for the rig, like when you have a skating board or something. So this kind of drilling rigs has something similar. When you finish drilling the surface part of the first well, you can push the rig to the something less than 10 feet. Something like 5 meters. So it is very small. Then I can have the wellhead of the second well. Then I push the rig again after I finish drilling the surface plate, the surface location, the surface part of the well, and drill the third one, the fourth one, and so on. Then after I finish the surface part, I go backward and I drill the intermediate. Then I go backward and I drill the lateral, the last one. So why we are doing this? To save money, to save time. Okay, we call that drilling pad. Look to the picture to the left. We have a lot of drilling locations beside each other. This is from a shale play. Can you imagine how much money we are investing here? It is billions of dollars. Okay. Okay, let me tell you something about shale completion. Okay, so shale completion. Whenever we say shale completion or unconventional completion, it means I'm talking about the hydraulic fracturing. Okay, so we don't have the same logic we use when we frac sandstone formation. Why? Because this is unconventional reservoir. It is really unconventional. So we have something we call complex fracture network. It means I need to fracture almost everything inside that shale. I should frac every single foot inside that shale. Okay, so we need to have something we call complex fracture network. I need to connect all this shale together. Why again? Because the permeability is very, very small, extremely low. So I need to frac everything. Look to these 2 wells, what we call zipper frac. You know, zipper in English, sorry. So zipper means, just something you have in your jacket. You know, in Arabic, we call it sosta. So this is what we call zipper. Okay, so I will tell you why we call it zipper. Because I start, look to the mouse, please. I start, perforating and fracking this zone. Then I move to the next well, the second well. Then I move back again to the first well. Then I move to the second well. Then first well, second well. So it looks like a shape of a zipper, like a Z shape also. Okay. So also when I inject a lot of fluid, I need to use a new term called stimulated reservoir volume. I need to have a volume that this is already stimulated, and this is already will produce a lot of oil or a lot of gas after opening that well for production. So in softwares, like frac simulators for shale, you will find something called complex fracture network or modeling of complex fracture network. Also, you'll find a volume, what we call SRV or stimulated reservoir volume. Also, one of the inputs you will use, the well spacing, which is the distance between the two laterals. This is the well spacing. You know, near the surface, all the wells are beside each other, like maybe 6 wells or 10 wells or 12 wells, they are beside each other, like few meters between the wellheads. But underground, you will find something like maybe 500 feet between the two laterals. Okay, so we call that well spacing. Okay, stages. What is a stage? Okay, to frac, I cannot frac all the horizontal section at the same time. Why? I don't have enough fluids to do it in the same time. I don't have pumps can do that at the same time. So operation-wise, this is not doable. So I have 2 teams working in the location. A wireline team do plug and perf. We call it plug and perf team. A second team, we call it the pumping team. This is the hydraulic fracturing company. So there's 2 companies working. Wireline company for plug and perf and pumping company for the hydraulic fracturing. Okay, so we I was trying to explain to you what is zipper frac, but let me wait for the next slide or the next 2 slides. Also, I need to think about the volumes injected. Okay, so please, I want to give you this question and try to think about it. Okay, what should be that I told you there's 2 companies working in the location, wireline for plug and perf and pumping company. If the pumping company working in a well, what should be the other company doing? Nothing. They are waiting. When the plug and perf company, the wireline company working, what should be the other company, the pumping company doing? They are doing nothing. They are waiting. Okay, so a lot of engineers we were trying to think about a way or a method to make these 2 teams working together at the same time. And they developed what we call zipper fracturing. So during the time that the plug and perf company working in well number 1 here. So the first thing I will do, near the toe, I will perforate using the wireline company. Then the pumping company will start injecting the first treatment here. At that time, the plug and perf company perforating the second well. Then the pumping company will go and frac the second stage in the first well. At that time, the plug and perf go back to the first well. So they keep switching together. So by doing this, you can keep the two companies busy 24 hours. So this is what we call zipper fracturing, because the 2 companies, they are keep switching together in the 2 wells at the same time. Okay. Let me tell you what is slick water. You know, when if you attended a frac job, we use something like jello, very viscous fluid. This is a frac fluid. This is a conventional frac fluid, right? If you don't see that before, just go to YouTube, write viscous frac fluid, and you will see something very viscous in a big jug or a big cup. And whenever you make it like this, that fluid start to very elastic, try to trip down in the ground. When you get it back, very elastic. Okay, so this is very expensive. That fluid very expensive. So around maybe 20 years ago, a guy from he's American guy, but his dad and mom from Greece. So he's Greek immigrant. His name is George Mitchell. He get on a crazy idea to use only water injected in a very high pressure, very high rate, around 100 barrel per minute. And to do that, there's a lot of friction in the tubing. To avoid that friction, he used a lot of friction reducing material, a chemical. So fresh water plus friction reducing material equal slick water. So this is what we call slick water. Slick water is very cheap, just a chemical and water. That's it. And he can pump up to 100 barrels in 1 minute. Okay, this make a booming success in Barnett Shale, and everybody start copying that experience, and all the companies start reporting that they get higher production after they did that. So they use cheaper material, which is slick water, and they get more production, which is amazing. Okay, let's go back to what is a zipper frac. I'm almost told you that the zipper frac, we were trying to enhance the efficiency of the operation. I told you there's two teams working, and whenever team number one work, team number two stay doing nothing, just waiting. And whenever team two work, team number one do nothing and wait. So developing the zipper frac or completing two wells at the same time, fracking two wells at the same time, what we call zipper frac, it was a way to enhance the operation efficiency. The good news that all companies, almost all companies, they did zipper frac, they reported higher production rate, something like 30% higher. So it was, amazing news. Okay, and I told you why we call it zipper, because we use, we go from well 1 to well 2, then we go back to well 1 to well 2, so it looks like a zipper. Okay, so here's like a summary about the advantage and disadvantage of a zipper frac. Again, we developed zipper frac to enhance the operation, but the good news that we get around 30% increase in the production rate. And so right now in the United States, there's a lot of activities for zipper fracking. Okay, so this is simply how we complete wells here in the United States. We do multi-stage fracking, like we frac, every single foot in the lateral section. We do them in stages, and each stage, imagine that example to make it closer to your mind. Let me go back to this figure. So look to the first well, well 1. Okay, so these fractures, this is stage 1, and this is stage 2. This is stage 3. So one lateral consists of multiple stages, and each stage consists of many clusters, and each cluster acts like one hydraulic fracture. Okay, so for one well, listen please. For one well, you can inject up to 4 million gallons of water. Sometimes reach 5 million gallons of water for only one well. So it means you need huge amount of water Even in Egypt, there is a river, but there is not enough water to do that. In Lebanon, I don't know how enough fresh water you have, but the bad news that in fracking we must use fresh water, which is a problem in many countries. In the United States, there is no problem at all in fresh water. It rains, all the year, and there's lakes everywhere, so there's no problem in fresh water. And this is one of the main reasons why we cannot develop organic shale in the Middle East. Libya and Algeria, they have huge reserve of shale gas and shale oil, but they don't have fresh water, so they cannot develop it. Okay, finally, I will start by my conclusion. Organic shale can develop millions and millions of oil barrels every day, and also, trillions of, standard cubic feet of gas every day. And it is very crucial here in the United States. We almost get like 50 to 60% of oil of United States production out of these shale plays. And as a summary, we should have a good brittleness, we should have a good TOC, we should have, the suitable, thermal maturity we want. And also we should have a good oil and gas price to develop it, because developing shale is more expensive compared with developing conventional reservoirs. I will stop here, and I'm ready to take your questions, please. So please, if you have a question, just write it in the chat, and I will read it, and I will try to I will do my best to answer it.
Thank you, Dr. Ahmed, for this amazing topic and interesting session. Actually, I have a question.
Sure.
What is the scientific reason behind the increased production by using the zipper frac and working on both of oils at the same time?
Okay, this is an excellent question. Look to this figure. Okay, first, at that time, we almost know nothing about complexity or complex fracture network. If you look to that first stage here, and the next stage in the well 2, they are communicating together. The fracture is the first stage, and the first stage in well 1 and the first stage in well 2, they are communicating together and increasing the complexity, increasing the passes inside the formation. So we get a better hydraulic fracturing treatment. That complexity, or that complex fracture network we created, we get more oil and more gas. And actually, we did not mean to get that. I mean, it was unintentionally. So when we did that, just we were trying to enhance the efficiency of the, just keep the two companies busy at the same time. But when we did that, because of that, integrate or reaction between the stages in the first well and the second well, they are staggered together and build that complex network between them, and we get more passes and better overall permeability, and we get more oil and more gas. Is it clear?
Yes, it's so clear. So we have a question from Melissa. Why we use fresh water?
Why we use fresh water? Because there's something, I believe you got it in your school, called formation damage. You may damage your reservoir. Damage your reservoir means there is that permeability inside the formation, and if you have any kind of bad solids, something not dissolvable in water, it can stuck inside these passes inside the formation and plug the formation. Okay, so why we use fresh water? Because if you use seawater, the seawater has a lot of salts, and this salt will damage your formation, will plug your formation, and ends up producing nothing. So you must use a fresh water with exact specifications. So whenever we get a fresh water in Egypt, in let's say in a location for Khalda Petroleum Company, we need to test that water. We check how much phosphate, how much iron, how much whatever, and we should decide if it is okay to use it in fracking, or we decline and reject that tanker. So the reason, if you use seawater or salt water, it will damage your formation and you will not produce anything. Or if we are optimistic, we will produce very little.
Muhammad Zain has the same question to you. We got the answer. What is the next question? I think Haris Ahmed is asking, is there any classification for shale on the type of organic matter it contains?
Okay, so the shale itself, I care about how much organic material I have. So if the what we call TOC, so if the shale is, let's say, 1%, the TOC is 1% or 2% or 5%, you need to decide that 5% is good for you or not, because maybe you have 5%, but the price is very, very low. So if you develop, you will not get money back from that business. Okay, so all the time, whenever you do something, you connect that with the oil price. Is it good or not? So the TOC, it tells you something about how much organic matter you have, and the thermal maturity, the value for the thermal maturity will tell you something about the type of that hydrocarbon. When you frack it, you will produce oil or condensate or gas. So we care about the TOC, the total organic carbon, and the thermal maturity. This will give you enough information about what you are asking for.
Mustafa Tarek is asking about, can we apply acidizing to produce from shale?
Yes, sir, we can do that, but we use some acids at the beginning of frac job, of fracking every stage, to lower the breakdown pressure. And you do this only if that shale includes a good amount of carbonate. Let's say if you have a shale and there is no carbonate at all in that shale. So why you are using acid? The acid will not react with anything. Okay? If you have good amount of carbonate, you can use some HCl at the beginning of each stage you are fracking. Why? To lower down the breakdown pressure of the formation and save some money out of the horsepower of the pumps you are saving.
Okay. Abdulrahman Morgan is asking, is shale good for oil? I don't think we have a clear question.
There is shale produce oil, and there is other shale plays produce gas, and there is some other shale plays produce condensate. So a state like North Dakota, they have a big shale play called Bakken, and they produce more than 1 million barrels of oil every day. In Egypt, they produce like 700,000 or maybe 600,000 barrel of oil every day. So North Dakota, out of that shale, they produce double of Egypt production of oil every day. So you can produce oil or gas or condensate based on the location and the thermal maturity of that location.
Sharif Muhammad is asking about, can we reuse the injected fresh water after the well is put on production and fracturing another wells?
Yes, we do that. There's a flow back whenever we frack the well. As I told you, we inject like 4 million gallons of water for only one well. So whenever you open that well for production, you get like 30, 40, 50% of that water back as a backflow. So we can take this water, do some treatment to make it reusable, or so I can reuse this water in new fracs. Or if not, if it is expensive to do that treatment, I can inject it as a disposal, or send it to a water flooding project or disposal. But yes, we use portion of that water we inject. When we get it back, we use it again.
So William Sayer is asking, economically speaking, do you think the shale industry can survive a long-term low oil price, and what are the possible ways to decrease the break-even price?
Okay, I mean, below $40, shale should not survive. But the situation in the United States, very special. The government help and support these producers to survive. So you see oil of $10 or $20, and they're still producing. Why? Because the government of the United States, they are supporting them. They even, if they can get cheaper oil from Saudi or from Kuwait, they will not do that, and they will keep supporting their, smaller producers here in the United States for, for political reasons and, for economic reasons, but again, Saudi in 2014 and OPEC, they were trying to stop or kick these small producers here in the United States out of business, but they failed to do that. Why? Because the government of the United States supporting these small companies.
Nizar Al-Hakim is asking about the challenges that we face in the environment for the zipper fracking.
Okay, fracking, in Europe, in many countries in Europe, they stop fracking. Why? Because we use a lot of chemicals, and these kind of chemicals may harm the environment. But here in the United States, there's one of the candidates from the Democrats. She was, her name is, I believe, Elizabeth Warren. And part of the program, she said, hey, I will ban fracturing, hydraulic fracturing. If I win, if I become a president of the United States, I will ban fracturing. When she said that, everybody started laughing. Do you know why? No one in the United States is ready to lose 60% of the country production just because a lady liked to support the environment. This is maybe a nice statement, but not to lose 6 million barrels of oil every day. No one will like that. If you do it, millions of people will lose jobs. So in Europe, it is a different situation. Here in the United States, there is two big political parties, the Republicans and the Democrats. Both of them, they are business oriented, and both of them, they are economic oriented. But in Germany, for example, there is a green party, green political party, and even if the, let's say, the prime minister or whatever, the guy who controlling the country, trying to stop banning the hydraulic fracturing, these political parties will refuse because the environment political parties in Europe, they are very strong and they have a lot of support of people. But in the United States, no. There's no, only the Republicans and Democrats, and both of them, they like to have jobs and business, and both of them, they don't care much about environment. Sadly to say that.
Bassam El-Ghul is asking about the additives. What kinds of additives that we add to the fracturing water, to the slick water?
Okay, the slick water, there's many materials we use. We call it friction reducer. This is just a chemical to reduce the friction with pipes. So there's a lot of different chemicals can do that. Imagine something very simple. You know what is glycerine, right? So imagine that we are getting some of this glycerine and we add it with water. We make that water a little bit viscous or a little bit, slippery. So whenever it goes in a pipe, it will reduce the friction. So it is just a type of chemical can reduce the friction between the water and the pipe and make it possible to pump up to 100 barrels per minute, which is not doable if you are not using a friction reducer.
Okay. Sharif is asking about, in the geological analysis, do we care about S1 or S2?
The S1, S2, S2, and S3, this is the pyrolysis analysis. And when you get them, it will give you something, it will tell you something about the type of hydrocarbon you have in that formation. There's one big question mark. If we develop here, we will produce gas or oil, because simply they have two different prices. You like to have oil, right? Because oil most likely more expensive. Make sense? But
Yes.
to do your evaluation, you need to know exactly what should be the something you are producing, because later you will sell it and get some money, and you need to evaluate how much money you will get. So the S1, S2, S3, this is not geology. This is evaluating the type of fluid of hydrocarbon you will produce. Geology will help you to, when you do the basin analysis, for example, to know exactly where is your source rock, and how that migration happened, and where is the conventional reservoirs. And for sure, they do that for, for normal activity of the exploration team at any big company.
We actually have many other questions, but we are running out of time, so we will take a couple of questions more. Loai is asking why the Middle East has conventional reservoirs. I don't know if this what you mean from the question.
Yeah, I got his question. He is asking why we are producing conventional why we are not producing the shale, for example. There is many reasons for that. Simply, in Middle East, we have a lot of easy oil. In Saudi, it is easy to drill everywhere and get oil. So it is cheaper, okay? In Saudi, they don't have fresh water to develop for organic shale. There is a lot of tight sand in Saudi. There is a lot of shale plays in Saudi, but they cannot produce it based on today's technology. They need to wait until something big happens that, hey, in fracking, we don't need that amount of water anymore, or something like that to happen. So in Saudi, in Libya, in Algeria, for example, there is a lot of shale, but they cannot produce it, they cannot develop it, just because they don't have enough water. Also, they don't have enough horsepower. We need a lot of pumps in these locations. And why you invest in something very hard and difficult to get, and you have a lot of easy reservoirs you can develop. This is the Saudi story. They can produce up more than 10, 11 million barrels a day, easy ones. So why they go for developing shale right now? Maybe they will do later.
Maybe. Zaina Judea is asking, this is the last question. Clay is rich in radioactive elements and has a high gamma ray values as well.
Yes.
How do we differentiate shales from clays in log analysis?
Okay, so this is a very good question. Let me go back to that slide. So at that case, so during evaluating if that shale is organic or not, organic rich or not, is it this one? No. I forgot what is it, but anyway. Anyway, I remember what I should say. So the clay itself has high gamma ray, right? But whenever we have organic matter, and that organic matter also includes some extra uranium. So now we have extra radioactive material. So I'm expecting to see, something higher than average of radioactivity. So the gamma ray will be a little bit higher, but it is not only that. I need also to check the resistivity. If there is high resistivity, it means there is a hydrocarbon inside the shale. And this makes sense. Makes sense why? Because if there is a lot of water inside the shale, water has salts, and this will be conductive. So the resistivity will not be high. Whenever you have high resistivity, it is a good sign of having hydrocarbon. Maybe you have high resistivity just because you don't have any porosity. But when you check the porosity and you see the neutron and density, and you know that you have a good porosity, so it means there's only one chance that you have hydrocarbon inside the shale. So the gamma ray will tell you exactly this is a shale, and also you will expect to see higher, a little bit gamma ray. You will see higher resistivity, and this confirms there's hydrocarbon there. And you will check the neutron and density to check to see if there is a porosity or a storageability of that hydrocarbon or not. And as I told you, based on the information you have at that stage, later I will ask to do Geochem log, and I will ask to do an MRI log. Also, I will ask to do coring. And we do these things only in the evaluation stage. Whenever we know everything about that location, we will never do these things. And what we'll do, we will drill, frac, that's it. Drill, frac, that's it. Hopefully this answers the question.
Yeah, thank you, Dr. Ahmed, for your time and effort. This was a very interesting and outstanding session. Thank you so much for your time. And now we will take and capture gathering photos. So please, each and every one of you, please share your video with us. Doctor, please, can you stop sharing the screen so we can capture a photo?
Okay, let me stop sharing. I stopped sharing. Hopefully it works.
Yes, excellent. So please, everyone, share your camera with us. Few seconds, please. There are many closing their camera, so please, if you can share it with us.
I will stop the live stream. There's no need.